right. Today we're going to tackle something that sounds pretty complex but is actually, incredibly intuitive. We are talking about fuzzy logic, or what I like to call it, the logic of sort of. Let's jump in and see how this sort of thinking makes our technology a whole lot smarter.
So let me ask you a question. The room you're in right now, is it hot or cold? I mean, chances are it's not a simple yes or no answer, right? It's probably more like kind of warm or a little chilly, maybe even just right. The real world just doesn't fit into these neat little boxes.
And that's exactly the point. We as humans, we describe our world with all this nuance. We say things are kind of fast or a little bit hot. But a traditional computer, it doesn't get that. For a computer, everything is black and white, true or false, 1 or 0. So the big question is, how do we teach a machine to understand all these shades of gray that we use so naturally?
Well, the answer is fuzzy logic. And this image here, it really nails the core idea. Instead of a hard on-off switch between false and true, fuzzy logic works on a spectrum. A statement can be, say, 20% true, or 70% true, or even 95% true. It's a system that actually embraces ambiguity, just like we do.
Okay, so let's dive in and explore how this way of thinking helps machines see the world a little less like a computer and a lot more like a person.
Just look at the difference here. On the left, you've got classical logic. It's like a light switch, right? A car is either slow or it's fast. There's a hard line. But on the right, that's fuzzy logic. The concepts of slow and fast actually overlap. A car can be a little bit slow and a little bit fast at the same time. It has what we call a degree of fastness.
All right, so this idea feels right. It's intuitive. But how do we actually, define it? How do we make this idea of fuzziness into something that a machine can actually use?
Well, here it is, the formal definition. Fuzzy logic is a way to reason where truth isn't some absolute, it's a partial value. It's a degree of truth, somewhere on that scale from 0, meaning totally false, to 1, meaning totally true.
Let's go back to that temperature example, because it makes it crystal clear. With classical logic, you're stuck. It's either hot or it's not hot. That's it. But with fuzzy logic, now we can get descriptive. We can say the temperature has a hotness value of 0.2, slightly warm, or maybe 0.9, which is very hot. It's just so much more precise.
Okay, enough theory. How does this actually work? How do we actually calculate one of these fuzzy numbers? Let's get practical with a real example.
So this formula you're seeing, it's called a membership function. It's really just a simple rule that we create to assign a fuzzy value. According to this rule, if a car is going 40 kilometers per hour or slower, its degree of fastness is 0. It's just not fast. If it's going 50 or more, its degree of fastness is 1. It is definitely fast. Right, those are the easy, clear-cut cases. But what happens when you're in that fuzzy zone, that gray area between 40 and 50? What about a speed like, say, 42 kilometers per hour?
Well, we just pop the number 42 right into the middle part of that formula. You take the speed, which is 42, subtract 40, and then divide the whole thing by 10. The math is super simple. And what do you get? You get 0.2. And there's our answer. At 42 kilometers per hour, the car isn't just not fast. It has a degree of fastness of 0.2. It's a little bit fast. You could even think of it as being 20% fast. See? When you break it down, it's not so complicated after all.
Okay, so now we know how to get one fuzzy value. But what happens when you need to combine a few ideas? Like what if a car is fast and close? Let's look at the basic rules that make that possible.
It really just comes down to 3 basic operations. And they're probably going to look pretty familiar to you. You've got and, or, and not. They work a little differently here in the fuzzy world.
And the logic is actually surprisingly simple. For a fuzzy and, you just take the minimum of the two values. So if A is 0.7 true and B is 0.5 true, the and result is the lower one, 0.5. And for a fuzzy or, you just take the maximum value. In this case, that'd be 0.7. That's it. And the last one, fuzzy not, well, it's even easier. It's just 1 minus whatever your value is. So if the truth of A is 0.7, then the truth of not A is simply 1 minus 0.7, which gives you 0.3. So why does any of this matter? I mean, why are we talking about it? Well, it turns out these simple rules, they're the engine behind some of the smartest technology that we use every single day.
And really, this isn't just some abstract thing we talk about in a math class. Fuzzy logic is probably already in your house right now. It's the brains that let your washing machine adjust the wash cycle based on how dirty the clothes are. It's used all over the place in robotics, and it's a huge part of many modern AI systems.
Here's a perfect real-world example: a smart air conditioner. It takes in fuzzy inputs, like the degree of hotness and the degree of humidity. Then it uses a simple rule, just like the ones we've been talking about. And that and you see in the rule, that's the fuzzy and operation we just learned about. It just takes the minimum value of high temperature and high humidity to decide exactly how strongly to blast the cold air. It's just more efficient, and it feels more natural. And really, that's what this is all about. By embracing the sort of and kind of parts of our world, fuzzy logic gives machines a way to make decisions that are more nuanced, more intelligent, and ultimately a lot more human.
So, now that you've got the basics down, I'll just leave you with this question. Think about it. Everything from medicine to finance to controlling traffic. What other complex problems out there could be solved, or at least made a little better, if we just let our machines think in shades of gray?